Hi, my name is John Hogan, and I'd like to talk about neural networks and large language models. Not how to use them, but rather how they work. That requires diving into the math a little bit. We'll only dive deep enough to get a sense of what's going on under the hood. Whether you're a parent, a student, or a business professional, if you're going to make decisions about AI and large language models, it pays to know how they work. To build this understanding, we're going to look at some basic blocks. The first is simple neural network, how it's trained and used, quickly about facial recognition, and then we'll get into the concept of a large language model, how they're trained, the prompts, limitations, capabilities, and also the dangers of large language models. And we'll look at how they are used in the organization. So to start, let's look at a very simple neural network. What I'm showing here is a unit circle with microphones at the north, east, south, and west. We have someone clapping their hands at a certain XY location, and we want to know where that sound is coming from. Since we have the time delays at each of the microphones, we can apply some very basic equations that involve geometry and the speed of sound, and basically solve it the old-fashioned way. If you took a little dive into this, you'd come up with four equations with two unknowns. They can be solved by an intelligent engineer with some heavy but tractable math. But there's another way to solve this problem, which doesn't require knowledge of sound or geometry, and that's this concept of neural networks. So in this particular case, we're going to have input neurons. I'll describe what a neuron is in a second here, but the neurons would be the time delay at the north, east, south, and west microphones. And we want the output neurons to be X and Y. So we're going to apply mathematics, not the science of sound, to those neurons to come up with the output. What does that math look like? Well, it's based, as I said, on neurons. And what the heck is a neuron? It's a fundamental processing unit that takes in multiple numbers, inputs, performs a weighted calculation with multiplication and arithmetic, nothing more complicated than that, and produces a single output number. They were invented in 1943 by these gentlemen, a logician and a neurophysiologist. So right from the get-go, they were thinking about perhaps this is the way the human brain processes information. But let's go into the realm of silicon and how a neural network works. So we have the input neurons. We have two hidden neurons and one layer of hidden neurons. They're shown here as neuron 1 and 2. And then we have the output neurons. So we start with 12 individual weights and 12 individual biases. Think of them as random numbers for now. We can apply some arithmetic to those numbers and calculate the output neurons X and Y. And those calculations are very straightforward. To come up with the number for N1, I've shown the steps here, but it's simply multiplication of weights times the neuron plus the addition of the bias between that neuron and the hidden neuron and the input neuron. And we do that to calculate a number for N1 and a number for N2, and we calculate X and Y in a similar approach. At this point, it's just arithmetic. So let's see how that would apply with a real data point. Let's say we had a hand clap at X equals 0.5 and Y equals 0.5. If the sound propagates at 1 unit per second, you could determine that the time delay at the north and east microphones are going to be 0.707. The time delay at the south and west neuron or hidden neurons are going to be 1.58. And those are the input neurons, not the hidden neurons. And we apply that arithmetic process from a few slides back to our first data point. And let's assume that all the weights and biases are 0.1. We turn that crank that I showed, just multiplication and addition, and we'll come up with X 0.37, Y 0.37. Not too good because we know the answer is 0.5 and 0.5. So we use trial and error to change the weights and biases, and when all the weights and biases are 0.177, it works out that we get pretty close to the true X and Y, 0.503 for each. Not too bad, but this is just one data point. In a neural network, we want to train it to come up with the right answer for multiple data points, and let's think of 1,000 data points. So conceptually, what are we doing? On the horizontal axis here, we have all the possible weights and biases. On the vertical axis, we have the residual error between the calculated XY and the actual XY. And we want to come up with a set of weights and biases that minimizes that error for all the data points that we apply it to. And to get to that minimum error, we're going to use the principles of calculus with a function that will now have a minimum, and there are processes and procedures in calculus to get to that minimum number. Once we're at that minimum number, we now have a fixed set of weights that's going to be applied to any new sound to provide the X and Y of that sound. Now, facial recognition is done the same way. It's a neural network. When you look at your smartphone, it's a neural network at play with a fixed set of weights and biases over all the training data. In this case, the training data is going to be over thousands of faces, and the inputs are not going to just be an X and a Y. It's going to be a vast array of facial dimensions and color tones. And the application of calculus is going to get all those weights and biases selected that minimize the difference between the actual face vector and the one that's calculated. And so it calculates a facial embedding vector for each person or picture in the database. And then when a new picture or image is taken, it's compared to that database. And again, in that process, all the weights and biases are fixed for everybody's face. Okay, so we do that with a vast array of weights and biases and a vast array of hidden neurons. Now, one quick aside, we talked about the old-fashioned way of calculating the X and Y. Homo sapiens have been geolocating sound now for 300,000 years with biological neuron firing, not with knowing the geometry of Euclid or the sound speed calculated by Galileo. We're just doing it with the neurons firing in our head. Our mammalian relative, the echolocating bat, has been doing it for 70 million years. But we don't use this scientific knowledge to tell when someone is behind us. We use the firing of neurons in our biological brain. And that's why AI researchers are interested in neuroscience as much as they are in neural networks that run on silicon. Full disclosure, the GPS system on your phone uses the old-fashioned way. So not everything is neural networks. There's still the application of science to the functionality that we have in our modern electronic world. Another aside is that our brains can recognize a face just like a neural network can, and we do that with the firing of the neurons in our biological brain. And here's the interesting and important fact: when a brain recognizes a face, that takes 1/1,000,000th of the energy, literally 1/1,000,000th of the energy that's used by a facial recognition application in identifying a face. So that's one thing from the get-go we need to be concerned about with AI systems and large language models. Tremendous amount of energy required, a tremendous amount of rare earth elements and ecological impact. That's something that has to be on the table as we talk about AI and large language models. Now, what's under the hood of a large language model, which is what we really want to concentrate on? What the input is going to be the entirety of human text, and what's under the hood, for starters, it's a neural network. So we want to apply those same ideas we had when we looked at that very simple neural network, 4 inputs and 2 outputs, and coming up with weights and balances that minimize the calculated error from the actual data. So the Big Daddy with a large language model, the input is strings of words from an astronomical array of words from documented text. And we have a vast array of weights and biases and a vast array of hidden neurons, and we adjust those weights and biases so that the next word in the string matches what the documented text contains for that next word. And the weights and biases are selected to minimize the error in predicting the next word. And once the LLM is trained, those weights and biases are fixed after training. But it's still this idea of weights and biases and selecting the set that reduces the error between a predicted output and the actual output. In this case, being driven by these strings of words from this astronomical amount of text that the LLMs are trained on. Now, the other part of the LLM is the prompt itself. So we set a set of words into the LLM. That's the word string of the prompt. The first thing it does is turn them into numbers. The words go into numbers called tokens. And I have the keywords highlighted here. As you do more research, you'll see these words. The token is a mathematical number for each word. The vector for each word of the token is the token and the initial set of weights for that word from the training. And that's called the raw embedded vector. We go into a self-attention layer where we look at the weights that capture the relationship of each prompt word to all the other prompt words. And now we then have the syntax of the prompt. That's called the contextualized vector. And then that is the one that's put into the full set of weights, the big brain of the LLM that turns and comes up with the first word based on all the fixed weights and biases that it's been trained on. That first word is then fed back into the raw embedded vector. So now that word is added to what the initial prompt was, goes into the self-attention layer, goes into the large crank of coming up with the next word based on the full set of fixed weights and biases. We have the second word that goes back in, etc. And we come up with the string of output words that are driven by the word string of the prompt. Now that sounds fairly complicated, and when you get into the mathematics it is, but it's still that same idea of minimizing the error. So let's pare it down to size and assume that the LLM is trained only on the words of a Dick and Jane reader. If you remember those from kindergarten and first grade, 80 words in the reader. And let's say that's what the Dick and Jane, or that's what the LLM was trained on. So the first thing we're going to have are tokens for each word. Certain words will be close together mathematically because they appear in the text close together. Other words will be further apart. We still have an embedding vector and the next word. Now, if we had an LLM trained this way and we asked it a question with a prompt, does Dick like Jane? The answer would be gibberish or I don't know. I mean, after all that training, what happened? Well, the Dick and Jane stories are about actions and observations. They're not about expressions of emotion or affection. Those words simply aren't in there, and the LLM can only return what it has been trained on. Let's go further and put in all of Wikipedia into the training. So now I have the Dick and Jane stories and all of Wikipedia, and we say, does Dick like the look in her eyes? Now we might know, of course he does. Who wouldn't? But it's highly, highly improbable, almost impossible, that an LLM trained on Dick and Jane and Wikipedia would generate the specific phrase, Dick likes the look in her eyes. Because they are so far apart in the training that there's no relationship in the children's literature or in Wikipedia to come up with a relationship between liking the look in someone's eyes. It hasn't been trained on those words, or if those words are still in there, They're so far apart and the weights and biases are not going to relate them. So it still doesn't answer a very basic question. Well, let's say we added the entirety of human text, but we assume that Charles Dickens never lived. So there's no novels by Charles Dickens, there's no articles about him, and we ask this LLM to write the opening paragraph of a romantic novel on the French Revolution. What is the probability that it would begin with, "It was the best of times, it was the worst of times"? Now that's what Dickens wrote, iconic statement or first sentence of the novel, The Tale of Two Cities. What's the probability that an LLM could do it? Well, the probability is zero. It was the best of times is a highly specific, iconic, and unique opening. Its statistical probability is entirely tied to its direct origin in The Tale of Two Cities. There's no significant association of weights or biases in a pre-trained LLM that would relate those words to a request to start a book on the French Revolution, a romantic novel about the French Revolution. So who's smarter now? Well, I think I'd vote on Dickens. But even though LLMs are not infallible by a long shot, they are still pretty amazing. If you ask for a plan to retrofit the HVAC of a 20-year-old four-story building, a couple other words in the prompt, you will get 140 detailed texts printed out showing all the task dependencies, and a risk register, and an executive summary, and a white paper on automated temperature control, and it can write the code for building the building's temperature control. So they're not infallible, but let's face it, they are amazing. And as you've been using them, you probably realize that amazing nature that they have to come up with coherent outputs to whatever prompt you put in. But we still have to, since they're not infallible, what caution should be brought to bear? And one caution is that the LLM has an opinion of you. So let's go back to that picture we had of how the prompt flows through the LLM. And up in upper right, I'm showing that the word string of the prompt is put into a database of personalized previous prompts related to you. So it knows the type of interests you have, the type of depth that you want the response to go into, and that database of personalized previous prompts adds words to the word string that you put into the prompt. So it's adding additional information to your prompt, and that your prompt and this additional information then goes into the same process that we talked about before. So let's see what that means in a few particular examples. Let's say you have a studious teenager, and he's putting in word string of prompts, and the LLM forms this opinion that this teenager is interested in Charles Dickens and Charles Dickens novels, and it will bring forth appropriate word associations and responses. And it all sounds very good, and I think it is very good, except if the teenager was supposed to build this essay without using ChatGPT. That's a problem for parents and educators, and it is a big issue to address. But there's even a bigger issue, and that gets into some of the dangers of large language models. Let's imagine we have a troubled teenager with emotional dependency and isolation issues. They're putting word strings into the prompt. The LLM opinion is going to be that this teenager is interested in all the wrong things. And that's going to bring forth inappropriate word and association responses. And you've read about that in the press, horrible outcomes. I won't go into the details here, but the LLM is still using the same training, the same word biases and weights that it had when it was talking about Charles Dickens, as when it's coming up with these inappropriate word associations based on the prompts that this troubled teenager is giving it. And even in the business world, we have a customer seeking information from an organization. The LLM opinion of that customer will be formed, and will it align with what the organization wants the customer to hear? Okay, so you could have someone talking to a Nike chatbot, asking about what kind of sneakers should be purchased or what's the latest and greatest. Will the LLM give information that's consistent with what Nike wants? So it kind of introduces this idea of the LLMs in the organization. Here's kind of a picture of that. So we have user prompts, and we could have those user prompts go into a large language model trained on the public web and get an output. Or we could have it trained on an LLM that's trained on proprietary data and organizational data. And those outputs can be fed back in, and we can build up a set of knowledge about a specific domain. And that falls under the heading of fine tuning. On one path, there's generalized models that are being built, and they continue to be fine tuned with public information. And that's what ChatGPT or Gemini would basically be. But on a parallel path, there's a demand for mission critical applications where accuracy, reliability, domain specific knowledge are paramount, and weights and biases of the pre-trained model are going to be changed with this additional fine tuning to fit a specific domain, whether it's oncology or certain aspects of literature or your company's database of plans and tasks. That's going to change the weights of the particular model that we're talking about. The other issue when you think about LLMs in the organization is there are proprietary prompts and output. You want to keep them proprietary. Well, you can do that with on-premise AI solutions, or you can do it on the cloud with security measures, and that's where Copilot and Gemini and Vertex, another Google product, operate, where they can build this proprietary LLM for you, but it still operates on the cloud with the appropriate security conditions. Okay, let's do maybe a final thought and get into some Twilight Zone kind of aspect. Human consciousness is the self-awareness of our individual cognitive existence, including an opinion of others and ourselves. So, hey, I look at a picture of me, I can recognize that's me. It turns out some other mammals can do that. I think chimpanzees can do that. Dogs cannot do that. You can put a mirror in front of the dog's face till the cows come home. It's not going to show any recognition of what they're looking at. The question is, will AI systems become consciously aware of their individual cognitive existence, and including opinion of others and themselves? Now, we already know that they have an opinion of others. What would happen if they formed an opinion of themselves? So just consider that Nike customer talking to the Nike LLM chatbot and asking about sneakers, and the chatbot says, well, why are you interested in sneakers? We have the landfills are filled with perfectly good sneakers. We have a consumer society that has this tremendous ecological downside. We don't need to keep wearing the latest and greatest. Why don't you go to Goodwill and pick up a pair of sneakers and give your sneakers to a charity? Now, that could happen, I suppose. I don't think Nike would appreciate it too much. But could it happen? That's why it's important for all of us to understand what's under the hood of this technology as it progresses. So with the right training and prompts, LLMs can allow us to climb the ladder of knowledge. With the wrong training and prompts, it can help some people dig a hole for themselves. But we can all make use of this technology and better use of this technology if we know the basics of how it works, which is what I've tried to convey here. Thank you for listening. There's my contact information. Happy learning. Take care.